We are starting our extra lessons for grade 9s. This is a live recording, so there are going to be questions and giggling. Commence with your question.
Ma'am, for the last discount. Okay, for the last discount that and whatever. So for the percentage we say big minus small over small times 100 over 1. And then for like how much does the jacket cost on sale, like the actual amount, how do we work that out?
Well, on sale, what does that tell you? Is that an increase or a decrease? If it's on sale.
It's a
It's a decrease. So you're going to use percentage decrease formula.
yes.
So you're going to take a number. I'll write it here for you. Percentage decrease, remember. Anything that's one you want to work out the sale price is always decreased. So you're going to say the number times 100 minus the percentage all over 100. There's the decrease. Remember, do we actually write 5%? If that was the, no, we just write 5. Why do we put the percentage in? It's already over 100. Very good. Okay. Has that answered your question? Yes.
Could you say 95 or not?
Straight away, of course you can. You don't have to physically show me that. Okay, good. Okay, let's start with exponents and then go back to questions. Is that okay?
Yes.
So, here you're opening up your workbook to exponents. And we're going to have a look at we're going to have a look on the first page. We're going to start exponents. Yes.
We didn't do dividing by decimals.
Okay.
Yeah.
Can we do exponents?
And then
Work and then go back. Is that okay? Because for me, this is the most important part, but we will go back. But I want to spend most of our time looking at exponents. So that's what we have. And it says, let me get a pen out. In B, when I multiply or divide, I use exponent laws. With exponents, I always look for like bases. Right, this is interesting. What do we mean when we look for like bases? So, where's she doing?
She's not there.
Okay. Bases that are the same. So, in your book, write today's date. Disclaimer, the board is being videoed, not your face. Right, today's date is the 6th of the 4th, 2021, and we are looking at exponents. Right? Please remember that note. I only use exponent laws, and we'll talk about the laws, right? But I only use law of exponents or exponent laws, same thing, differently phrased, when I multiply or divide. Important. Who can tell me what happens when I add or subtract? Side note. What do we do when we add or subtract?
you just it's like something
We look for like terms. Right? So let's look what I mean by, okay, must I pause for you to write?
That's fine.
Okay. So law of exponents, when I multiply or divide, when I add or subtract, I look for like terms. Both of them is a form of algebra because we use letters. Or what is a better word for letters?
Variable.
Variables. Very good. Okay, can I clear this or not yet? Variables. So I'm going to do a very brief explanation of like terms and like bases. Can I clear it? Okay, so when I am, let's do adding or subtracting, right? I look like. Now, look at my color coding, because I'm going to do a table, by the way. If you want to pre-plan, I'm going to do a table. I look for like terms. What are like terms? Okay?
Should I put this on the table?
No, you can put it here. Thank you. Has everyone signed?
Yes.
Thank you. What are like terms? Like terms are as follows. 2x plus x. Right? These are like terms. Who can remember what this answer is?
3x.
3x. Very good. These are like terms. What are unlike terms? Just so we can understand. If I said to you 2x plus x squared, can I do anything with that? No. So the most important part about like terms is that the variable and the power must look the same. So that's what makes like terms. It's the variable and the power must be the same. So you see these are unlike terms. Why? Why are these unlike terms? Different powers. Very good. Can you not go to that table? It's being recorded. So, yeah, that's fine. Different powers. Does that make sense? Okay, so that's when I add or subtract. Okay, now I want to talk to you about what happens when I multiply or when I divide. Right? When I multiply or divide, I need to look for like bases. Now I hope I can put this all onto the screen because I want to use the exact same thing. Now like bases is just the variable. Over here we wanted the variable and the power to be the same. But here we just want the variable to be the same. So I'm going to use exactly the same here. I'm just, instead of adding, I'm going to multiply. Okay, so what does that mean? Instead of saying 2x plus x, I'm going to say 2x times x. Who can remember what the answer is to this? 2x times x.
3x.
That was when I went 2x plus x. But down here, 2x times x? 2x squared. Do you remember that, Bailey? Okay. Versus here, instead of saying 2x plus x squared, I'm going to say 2x times x squared. When I was adding or subtracting, I couldn't interact with those two variables because they were different terms. But what can you tell me about these here when I'm multiplying? The variable is the same. So therefore I can interact. You see here I have x and I have x. I don't care about the squared. Who can tell me, can you remember what the answer is to this?
2x squared.
2x cubed. Very good. So when I add variables that have different powers, you can't do anything with them because they're called unlike terms. But when I'm multiplying, as long as the variable is the same, they can interact with one another. Okay, so it's very important to decide, am I adding or subtracting? If you had to think of BODMAS, remember it's brackets of, who cares, addition and subtraction. Remember I spoke about addition and subtraction being one thing that you can do. And then multiplication and division. So that's what it comes down to in algebra. That if I'm multiplying or dividing, the variable and the power must be the same. And I just stick it all together with the same variable slash power. Okay? But when I'm adding and subtracting, when I'm multiplying or dividing, I just have to have the variable the same. Keep the variable, add the powers. Do you remember one of those laws? Okay, so when we're multiplying or dividing, this is where we use exponent laws, exponents. We don't do exponents ever if you're adding or subtracting. If you're adding or subtracting, you add together everything that is exactly the same. Full stop. That's all you do when you add or subtract. Here I added together everything that was exactly the same. How many x's did I have? 3. see that? 2 x's and 1 x, I just have 3 x's. So I didn't do exponents because I wasn't multiplying or dividing. Okay, do you remember this at all?
Yes.
Good. So, let's look at what I mean by like. Are you still copying? Okay, let's look at what I mean. I know it's frozen, let's just wait. By like bases. Can I take it off yet? Is there someone saying no? Fine. Like bases. Yes.
In the plus and minus, right, with this exponents, you also add the exponents.
No. Only when I'm multiplying or dividing do I interact with the exponents.
Oh.
If I'm adding or subtracting, they have to look exactly the same. Otherwise, I can't do anything with them.
Oh.
Okay, yes, you know.
Is this still in the table?
No, now I'm done. Sorry, my table was split one on top of the other. It would have been cool if you did it next to each other, but I didn't have the space. Like bases. So what do I mean by this? Right? Or let's just talk about bases or exponents in general. If I had x to the power of 2, here we go. This is my base. That's all I look for. That must be the same. Does that make sense? It doesn't matter what this is. This is called my power. Together, what do I call them? Exponents. Very good. Together, they're called exponents. But individually, and when do I use exponents? When I multiply or divide.
Yes.
Okay. Right. So, that's the base that has to be the same when I multiply or divide. The power can be anything. So, like bases would be, for example, this. X to the power of 5. Same base, different power. Or x. Same base. What is the power here, by the way? 1. Very good. So these are like bases. Does that make sense? Unlike bases would be something like this. X squared and y squared. Why do kids get confused? They think they can do something because the powers are the same. But different bases, unlike bases. So you cannot do exponent laws. You can only do exponent laws when the bases are the same. Okay, what is the base? The variable. Or, please don't forget, that an exponent can also look like this. Can I take this off yet?
Yes.
Someone say no. Right? Exponents can also look like this. 3 to the power of 2. Base, variable. Give me a like base to this. 3. Thank you. Another one.
6.
Why is he incorrect?
Because it's not the same.
6 is not the same as 3. This is 6 to the power of 1 and 3 to the power of 1. The bases are not the same. Give me another one.
3 to the power of 4.
3 to the power of 2021.
Yes.
Does that make sense? These can all interact with each other. Where do kids go wrong? I'll show you where they go wrong. Okay? Unlike bases would be something like this. 2 squared and 3 cubed. So these are unlike. Can I do anything with these?
No.
No. Unless I physically worked them out and got rid of the exponent. Do you understand what I mean by getting rid of the exponent? That it was just like a whole integer. But as exponents, you cannot do anything with this because they are different bases. So please don't forget, exponents can look like a variable with a power, or it can look like a number with a power. These are both exponents, and they have to have the same bases in order to interact. Okay, do you understand what a like base is? Excellent. So let's look at what our exponent laws are. And remember, when can looks like this. The first law, there's like 4.2. The first law, and I'll never say to you, what is the first law of exponents? Does that make sense? I'm basically just telling you 5 things that you need to remember about exponents. I'm never going to ask you a theory question. What is the third law of exponents? No. The first thing you need to know about exponents is when I am multiplying. So, when I multiply, keep the base, add the powers. That's a multiply, not an x. That's the little song I sing to myself. Keep the base, add the powers. Keep the base, add the powers. Right? So, an example of this would be, let's go, y to the power of 3 times y to the power of 5. What is my answer? Keep the base. What is my base?
Y.
Add the powers.
8.
8.
And what if it's in plus?
What if it said plus? Could you do anything with y cubed plus y5? Why not?
Because the powers are.
Unlike terms, the powers are different. Remember, I can only do exponents when I am multiplying or dividing. Okay. Another way that this could look would be a to the power of m times a to the power of n. Multiplying, same bases. What do I do?
A-N.
Keep the base. Read this. Keep the base. Add the powers. So what would it be? A?
M-N.
No.
N-M.
M plus
Thank you. M plus n.
M&M's.
Keep the base. Add the powers.
Is that the answer?
Yes. Just like here, you literally said y3 plus 5 and you wrote it as y8. This is m plus n. Okay, that's the first rule. Are you with me?
So man, you don't write the M-N. You just
What? Just tell me, what does, yes, remember mn means m times n. That's not it. The rule is keep the base, add the powers. Okay, right. Cool. Next law of exponents, or in other words, the next thing that you need to know about exponents is when I divide. Okay? So, the rule is keep the base. Who can remember? Minus or subtract. Subtract the powers. That's the rule. I don't know. Tomorrow morning, probably. Okay. Right. So, what does that mean? For example, if I had y to the power of 5 divided by y to the power of 3. Just like we had earlier, y 5 times, what would the result be?
Y2.
Y, keep the base, subtract the powers. So if we used our other example, a to the power of m divided by a to the power of n, what is my answer going to be?
M-N minus N.
M minus
A to the power of power minus power. Done. Here's a nice one. What happens if I gave you this? 3 to the power of 2001 divided by 3 to the power of 2000. What would your answer be?
3 to the power of 1.
3 to the power of 1. Keep the base, subtract the powers. Yes.
Could you just write 3 there?
Of course you can. I was just showing you that there's the 1 because 2001 minus 2000 is 1. Yes.
Ma'am, will you ever get like a negative power?
You are going to in grade 9. So in grade 8 you didn't get the negative powers, but in grade 9 you will. Okay. Right. The third thing you need to know about exponents is when I have a power raised to a power. So I always think of that emoji. I'm not an artist. Power raised to a power. You know what emoji I'm talking about? Power raised to a power. Right? The muscle arm. This guy's got no muscle. Right, or girl, who knows? There. Power to power. Right? And what you do is, this is your little tune. Keep the base. You see how it's important to understand what a base is? Everything. Keep the base, keep the base, keep the base. In this case, it's keep the base, multiply the powers. So for example, if we use our y example of y to the power of 3 raised to a power of 5. You see the power to a power? Yes. Keep the base, multiply the powers. Power, this is my little dance that I do, dance. Power to power, we multiply. It's like you increase strength because you've got 2 powers. Right. Okay, and let's use our other one. What happens if I had a to the power of m raised to the power of n? Thank you. A-M-N. Very good. I'm going to stop using some numbers because kids get terribly confused when we all of a sudden use numbers. But if I had 3 to the power of 3 raised to the power of 2, what would my answer be?
3 to the power.
Thank you. Keep the base and the powers. Multiply the powers. What do you think kids do wrong here?
They add.
Sometimes they go 3 times 2 is 6, and then they say 6 to the power of 3, or they say 3 squared is 9, and then they say, I don't know, it's weird. But this is also an exponent. You see the base with a power, that's an exponent, so I can use exponent laws. Okay. Right. The fourth thing you need to know about exponents, and we're almost done now for revision for grade 8, well not revision, but what you should have known already, is if I have, can I take this off? Important, a monomial raised to a power. A monomial raised to a power. Josh wants to know, what is your name? Daniel, sorry. Daniel wants to know, what is a monomial? So let's look at examples of monomials. What is a monomial? One term. Very good. So an example of a monomial would be x. What other examples do we have of monomials? 4. What about 4x? Is that a monomial? Yes. This is one term. Because what joins things together? No, timesing joins things together. What separates things?
Divide.
Adding or subtracting. No, guys, you forgot about BODMAS. Please don't get up. There's the camera rolling. Yes.
I didn't know you were teaching.
Yes. Right.
Who are you teaching?
My grade 9s.
Are they writing tomorrow?
They're out on Thursday.
Jason needs to speak to you urgently.
Oh gosh. Okay.
It's to do with the grade 11 lesson.
Oh no.
Yeah, I told you.
Okay. I asked. Okay, okay, right. I'm gonna finish this, give them something to do, and then I'll run and see her.
Okay, she's in her office. They're busy setting the grade 11 test.
Okay. Right. Kids, so remember you were talking about what joins things together? Remember I said to you division and multiplication are one thing. They join things. And addition and subtraction, they separate things. Okay. So this is indeed a monomial. Right? Another example of a monomial is x times y. Why would x times y be a monomial?
Because
They join together. Very
So
good.
you'll see when you finish. Please.
Really?
Yeah, I think she wants you to post something on about numbers that's inside. You must see it. But they're still there.
Okay, is that okay?
Yes.
Right. So, when I have a monomial inside of brackets, this is my tune. Bomb in to every
Number.
variable or number, or every, let's call it every base. That would be their math language. Okay, so I'm going to give you some examples. Example, if I had, for example, x squared y cubed raised to the power of 4. How many bases do I have?
2.
2. Is it a monomial?
No.
Yes.
Yes, there's an imaginary multiplier in between. So that means I bomb in. Now, remember, this is a power to a power. What do I do?
Time.
Power to power times. Very good. So what is my answer?
X8.
X8, Y12. Thank you. I multiply because it's power to power, so I must multiply. Using the rule for number 3, right? So it's actually not even a new rule. Another example I want to show you is what happens if I had A, B to the power of M. What would your answer be?
A.
A, M,
Times. B.
B, M. Good. You don't have to even put the multiplication in. But this is a monomial, so it must go to every base. Do you see the bases? Now this is where kids mess up in the next one. If I had to say to you 2, let's make it, no, let's not make it Z. Let's just make it 2x raised to the power of 3. How many bases do I have?
2.
2 bases. Remember I said a number can be a base? So 2 bases. So where did kids go wrong? They tell me the answer is 2, sorry. They tell me the answer is 2x cubed, and that is incorrect. Why? Thank you. It's 2 cubed times x cubed. The instruction is bomb into every base. Just like we went to the A and the B, here you must go to the 2 and the x. Okay, it's still a monomial, so it must go to every single different base there is.
Oh, nice.
Okay,
And what if it's not a monomial?
then you do something called FOIL, which you haven't learned yet. Okay, so it's important to remember, you won't get that now, but when we have learned FOIL, it's important to remember that when it's not a monomial, I must do FOIL. Okay, right, and the last thing you have to remember, can I take this off, is the power of 0. I got the power! Woo! Right, what happens? The base becomes 1. What's that? Polynomial? Poly meaning many numbers. Monomial, 1 number. Right, so here we go. The base becomes 1. An example of this would be x to the power of 0. Now, who does the 0 belong to? X. So the base, which is x, must now become 1. Another example, what happens if I did this? Who does the 0 belong to? The x. So what must become 1? The x only. So this becomes 1. What's your answer? 2. Very good. 2 times 1, which is 2. Okay. What happens if I gave you this? Who does the 0 belong to? Both. The bracket. Do you agree? So what must become 0? Oh, sorry, what must become 1? Both of them. So it's literally going to be 1 times 1, which is just 1. Okay. So there's 5 things you need to remember. The first thing is, when I'm multiplying, keep the base.
Add the exponent.
When I'm dividing, keep the base. Minus. Power to power. Multiply. Question Number 4 is also still power to power, it's just making sure it's a monomial. And the last thing is the power of 0, which becomes 1. Very good. Okay. So what I want you to do, while I quickly go see Mrs. Swart, is I want you to, at the bottom of page 1, I want you to start doing number 1 to 9. Not 1, oh no, yeah, 1 to 9. There's one thing I want to mention before you start. Okay, this is what I want to mention. Remember this. Now this is separate, this is extra, hey? It's not an exponent law, but I just want you to remember. What is the difference between this, negative x squared, versus this? Who does the squared belong to in the first one?
It belongs to the x and the minus.
It belongs to the x and the negative. Very good. Belongs to the whole bracket. And what is a negative raised to an even number?
Positive.
A positive. So this answer is positive x squared, right? Who does the square belong to in this?
Just the x.
Just the x. So what is my answer here?
Negative x.
Negative x squared. Very good. Just hang on, Josh. Sorry, Daniel. Oh, wow, I call you Josh. I'm sorry. Dan the man. Right. Just look here. What would happen here? Negative y cubed versus negative y cubed. What happens when I've got a power a negative raised to an odd number? It stays negative. So my answer is negative y cubed. You agree? And here, who does the cube belong to?
The y.
Just the y. So it doesn't even affect the negative. It just stays negative y cubed. Yes.
You have a negative power.
Yes, and we're going to look at it now. So, what I want you to very quickly do you see exercise 1 at the bottom of your textbook? Your workbook?
Yes.
Okay, I want you to start doing number 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, I'm quickly going to go see Mrs. Swart. Will not be long. Sorry? I'm going to guess.
1 to 9.
You don't do 1 to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, stop.